Okay, so looking at the first one, which of the following is a counter example? So a counter example is something that's going to disprove this statement. So it says all people who get ATARs over 90 do extension to mass. So if you look at this, no people who get ATARs over 99 do extension to mass. Now we're trying to say that if all of the people, not just all of them, every single one of them, if they get over 90, then they do extension to mass. Okay, so that one's not going to disprove it. Jesse did history, so that's one person, and he got an ATAR over 99. So we want to do all the people who get over 99. That's just one person. Sam did extension to mass and got an ATAR, so that's not going to prove it. That like more or less proves it. Polly did not do extension to mass, but she did get an ATAR over 99. This one will disprove it because that's one person who got over 99.
It's 12 o'clock.
But did not do extension to mass. Okay, looking at this first things you've got to realize what a converse is. So if P implies Q, Q implies P, that's the converse. So you just swap them. Think of Converse shoes, and then you swap them. So it's just going to be back to front. So the converse, if n is prime, then n has exactly two factors. So if n has exactly two factors, then it is prime. Okay, so converse P implies Q, then Q implies P. All right, what is the contrapositive? So the contrapositive of P implies Q is not Q implies not P. Okay, so not Q would be, so let's just look, this is P. It's good when you start these off to set them up. So P is if n is prime, and Q is n has exactly two factors. Okay, so the contrapositive would be if n does not or doesn't have exactly two factors. So you do the negative of it, the negation of it. Then do you realize too that that symbol means not Q, not P. If n doesn't have exactly two factors, then n is not prime. That would be the contrapositive. So that's part 2 of A. So determine whether or not the statement is equivalent. So what does equivalence mean? So far we have the converse. So if you have P implies Q, the converse is Q implies P. The contrapositive, and the contrapositive is really useful for proving things. So the contrapositive would be not Q implies not P. So you swap them and you not them. Now this is actually a really useful tool for proofs, because the converse, when you swap it, the converse is not necessarily true. But the contrapositive, if you swap them and not them, then what that means is if not Q implies not P, then that will mean that P will imply Q, and you can use it to prove it. I'll just show you why, because if P implies Q, that would be if you're in P, then that means that you are definitely in Q. It's like if you're in Sydney, then you're in New South Wales. Okay, so if you did not Q implies not P, so if this is P, I'm just going to put a thing out here. If this is P and this is Q, not Q would mean, not Q would mean out here. All right, so not Q implies not P. And it does, because if you're in not Q, then you are in not P. So if that is true, then the original statement P implies Q will also be true. So not Q's out here, whereas not P is like all of this, and see how they overlap. So if you can prove a contrapositive is true, then you can prove that the original statement is true. Just in a quick example of that, if n squared is even, then n is even. It's much easier to do this by the contrapositive. So it's much easier to prove that n squared is not even. I mean, n is not even, which is odd, implies n squared is odd. And then if you can prove that that part is true, then you can prove that the original statement is true. So if you let n equal 2k plus 1, that's much easier than just doing a direct proof, because you have to let that equal like 2m. And when you do that, then you're dealing with square roots and things, which isn't as friendly to find n, you know, is that even? Like, that's just not good. So if you do the contrapositive and you knot it, it's a lot easier to do. So the contrapositive is n is odd, then n squared is odd. So that means n squared would be 2k plus 1 squared, which would be 4k squared plus 4k plus 1, which is 4k, k plus 1 plus 1. So what that means is this here, which is equal to 2, you can see it's even. That part there, that is divisible by 2. So you could say that's 2 times 2k, k plus 1 plus 1, or 2m plus 1, where m equals 2k, k plus 1, and m is an element of integers. Integers are z, so m is an integer. Okay, so what this is telling me then is that the contrapositive is true, because this is odd. Okay, so that means not Q implies not P. So the original statement, P implies Q, will be true, and just say that's by contrapositive. So you just state what you're actually doing. Okay, so let's go back to this question. So we're up to, we've written the contrapositive, we've done the converse. If you can prove the contrapositive is true, the original statement is true. What does equivalence mean? Okay, so let's think about what equivalence means. So equivalence is associated with P if and only Q, or it means this here. Okay, that's equivalence. To prove something's equivalent, you have to prove that P implies Q and Q implies P. Okay, so let's look at this statement here. I'm just going to grab it. So the question is this equivalent? And if not, give a counter example. Is that right? No, that's the other one. Determine whether or not the statement is equivalent. Give reasons. So is it equivalent? So P is n is prime, and Q is n has exactly, sorry, 2 factors. Okay, so to prove it is equivalent, that means we have to prove that P implies Q or Q implies P. So it works both ways. So n is prime, then n has exactly 2 factors. Is that true? Yep, because if n is a prime number, it has 2 factors, 1 and itself, for it to be prime. So this part here is true. Q implies P. All right, so that means if n has 2 factors, then it is prime. So it's exactly 2 factors, okay, not just exactly. So that is also true, because anything with more than 2 factors will actually be composite, like 6, for example. 6 has 6, 1, 2, and 3. A prime number only has 1 in itself, like 3 would be 3 and 1, 2 would be 2 and 1. So if it has 2 factors, that will actually mean that, yeah, it is prime. If it has more than 2, if it does not have 2 factors, then it's not prime. Just note here, because this comes up in the next question, that 1 is not prime or composite. And 1 has 1 factor. Okay. All right, so the third part of this is We've done that part. George's statement. Now let's look at George's statement. Okay. All right. George's statement. Okay. So George, if n does not have exactly two factors, then n is composite. Okay, so P is n does not have two factors, and Q is n is composite. So determine whether or not this statement is true. And if not, give a counter example. Okay, so just have a quick squig. Where am I up to? Okay, where is it here? All right, so basically, if M does not have two factors, then it is composite. Now, is that true? Let's have a think about it. Okay, so 6 doesn't have two factors. That's 6 and 1, 2 and 3. Yeah, that's composite. Composite means it's divisible by more than 1 in itself. Okay, 9, yeah, that works for 9, 3, 1 and 9. But there is a counter example, and the counter example is 1. 1 does not have two factors. It is not composite, and it is not prime. It only has one factor. So that's your counter example. Okay, the next one, the meerkats. So what's the negation? All right, I'm just going to run through some things with negation because there's some important things that you should know. Now put the meerkat one just there. There's the meerkat one. Okay, so a negation. So if you want to negate the following things, if you want to negate P, it is just not P. Okay, so if you had P, then the negation of that would be not P, which would be out here. If you want to negate anything with for all in it, you need to put that one which is exists. This means for all, and this is there exists at least one thing where it's true. Okay, if you have a compound statement like an and or an or, and the symbol is like that, or the symbol is like that, negate and, you will get or. Negate or, you will get and. So for example, if P or Q will become, let's just look at, okay, for all X, an element of real, P or Q, if you negated that statement, that would be there exists an X, which is an element of reals, where P and Q, so you'd have to change the or to an N before or to there exists. Okay. The other thing, if you want to negate a statement that is an implication, so for example, P implies Q, then what you've got to remember, it's like this. You go, P is true, but Q is not. Now, I'm just going to find you an example on this so that I can make that really clear. Okay, if it is a cat, it has a tail. Okay, so if I want to negate that actual statement, the negation would be it is a cat, so you keep the P as true, but it has no tail. So you negate the second part of the statement. If it was just the cat is black, that's just like, that's not an implication, that's not P implies Q. Then the negation of that is just the cat is not black. What about if I study for my exam, I will do well in the exam. Okay, so we'll look at a few different things for this. Okay, so if I've got that, let's just focus on that. All right, so if I want to negate it, what that means is I studied for my exam, so keep the original statement, but I did not do well. Okay, if I want to do the converse, you just swap it. I will do well, sorry, if I do well in my exam, then I studied for my exam. Okay, if you want the contrapositive, that's swap and not. And remember, the contrapositive will always make the original statement true. And that's the power of it, because sometimes it's easier to do the two nots and swap it. The contrapositive would be, if I did not do well in my exam, then I did not study. Okay, that's the contrapositive. So contrapositive, converse, and negate. Okay, so let's go back to the meerkats. So negation, this is not an implication, it's just like a statement. All meerkats eat grubs. So there exists a meerkat, that's what that means. So there exists, exit, there exists a meerkat, or you could put at least one meerkat, that does not eat grubs. So if you're just going to check the wording on that, if they put, they're at least, yeah, it's at least one meerkat that does not eat grubs. Because if you have a for all statement, it goes to at least. So there exists, we'll do at least one meerkat that does not eat grubs. Okay. All right, let's keep going with this. So where are we at? This one here. All right, so this one here is a little bit tricky because we have a few things happening here and it's got an or and an end in it. So when you negate these statements, the ors have to go to ends and the ends will go to ors. Now in this, that has two ends, so you've got two different things. So let's just go P is M and M plus N are even, and Q is M and N are even. Now, not P would be M, N, or M plus N are odd. That's the negation of it. And not Q would be M and N are odd. Okay, so let's write the contrapositive. So the contrapositive would be not Q implies not P. So M and N, N shouldn't be N, that should be or, because an N goes to an or. N to or, N to or. M or N are odd. So if M and N are odd, then M, N, or M plus N are odd. Okay, so that's the contrapositive. Now you have to prove it. All right, so the or statement's quite interesting because it's an or. You would have to do two cases. So in order to do the cases, case one is M or N are odd. So that means if you let M equal 2k plus 1 and N equals 2k. See, it's an or, so there's not both together, whereas the and is both together. So if I do this first one here, then we have to show mn is odd or m plus n is odd. And we could also do vice versa, but it's going to be the same thing if you swap the m and the n. So you could just repeat it at the end. So let's go mn. So let's say if m, let's go, I won't put k there, I'll put a big, no, I can't put an m there either, we've used that one. I've got to put something else there. So let's put j. So 2k plus 1 times 2j. So that means that's odd, and that means that is even. So if m is odd or n is odd, if m is odd or n, that means that one's odd and that one's even. Then we want to prove that mn or m plus n are odd, not both of them. So it's kj plus 2j. That one gives you 2kj plus j. That one gives you an even, because that's equal to 2, let's go big B, where B is an element of the integers. Okay, that is even. So it's, we want to prove basically that mn is odd or m plus n is odd, one of them. So we know that m plus mn is not odd. Let's try this one. 2k plus 1 plus 2j equals 2k plus j plus 1, which equals 2a plus 1, where a is an integer. So therefore, that is odd. So if m is odd or n is odd, so we've got m is odd, then one of them will be, this one's even, and this one was odd. So we have to show that mn is either odd or m plus n is odd, and m plus n is the odd one. So I've actually proven that. Now it would be the same, you could just state it would be the same if you swap the m and the n. Okay, it's not going to make any difference because m times n is the same as n times n, and m plus n is the same as m plus n. Okay, so what's the other case? Is there another? So we want to go, if m or n are odd, okay, then mn or m plus n are odd. Yeah, so the other case would be if n was odd or m was even, and you could do the same proof, and you would prove that this was also true, that either n plus m or mn are odd, and then it will work. Okay, just gonna have a quick squig. Yeah, so I think that explains it. So therefore, not Q implies not P. So therefore, by contrapositive, the original statement is true. So that means that P will in fact imply Q. Okay, now the next one is a little trickier. This is quite, yeah, it's quite a harder sort of proof. But I think when we're looking at these, you're always looking at factors. So let's just put this one here, and I'm going to add in a page. Okay, so if we want to show that B and C cannot be integers, so let's go that C minus B and C plus B equals 4. Okay, so if I factorize that, that means that C minus B and C plus B, they must be factors. They must be factors of 4. Okay, so we're showing that it cannot be true. So that means that the factors of 4 are 2, 2, 1, and 4. So C minus B could be 4, or C plus B could be 4. C minus, I'm sorry, 1, because it could be 4 times 1, or it could be 1 and C plus B equals 4. So 1 and 4 go together, and 4 and 1. So this is 4 and 1, and 1 and 4. Or we could do 2 and 2. So C minus B equals 2, or C plus B equals 2. Now one of these if it fails and it doesn't work, well, then this statement isn't true. Okay, so I'll just take the first one there. Let's add them together. So if you did 1 plus 2 of that, you'll end up with 2 C's, and the B's will cancel, equals 5C equals 512, which is not an integer. Okay, so therefore prove that it cannot be an integer that is positive, a positive integer. Okay, so if you took this C and you put it back in there, you get 5 on 2 minus B is 2 minus B equals minus a half, B equals a half. So that is also not an integer. So therefore it also does not work. Okay, I think that one's probably the most confusing out of most of them, but it's, yeah, basically by looking at one of the cases, you know, they've got to be factors of 4, and solving one of the equations, you can see that it does not work for one. So you've actually found an example where it doesn't work. Okay, now when you're doing these questions, and there was one, if you look up the Nessa sample questions as well, consider the statement, if you have no treasure, I have no kingdom. Now, whenever you want to see if something's logically equivalent, what you need to do is prove that the contrapositive is true. Like, this will always be like the contrapositive. So if you want to show it's logical and equivalent, then if P implies Q, Q must imply P. So when you're looking for the answer of this, the one that will be exactly the same as that original statement will be the contrapositive. So that's what they're looking at. So if I have no treasure, then I have no kingdom. So if I have a kingdom, so you've got to not it. So you've got to do not Q implies not P. So which one, when you're looking at these, which one will be not Q implies not P? If I have a kingdom, then you have treasure. Not no treasure, but treasure. And that's because you're doing the opposite to these original statements, which is not kingdom and not true. Okay, so when you're looking at this next one here, which of the following is the negation of a statement? So with the negation, the for all will go to there exists. So there's the for all. So the only two possibilities are D and E to start with. And then it's an implication, so you're implying. So you've got to keep the original statement. So you say P is true, but Q is not true. So when you do that, P is true. So when you look at those two, the one that is true would be that one. It can't be that one because that one's got not. Then Q is not true. That's that one there. Okay, so you could use and as well as but because you want these two things to happen together.